Welcome. This is an hour-long talk where I'll be discussing some of my previous work and future work in the space of privacy as a service. My overarching goal in my research is to build practical cloud systems that protect user privacy from powerful threats. I think it's clear that user privacy today is inadequately protected. In fact, user data is compromised so much that the companies that we rely on to measure this can't even fit the numbers on the screen. So, what do I mean by a powerful threat to user privacy? Who's doing this? Well, today we live in a world of very powerful threats to privacy. We're talking about organizations with nearly unlimited budgets and potentially physical access to core infrastructure. So, some very real examples today are organizations like organized crime and nation state actors. And we know that they're doing things like gathering intelligence, covert surveillance, cyber warfare. In no uncertain terms, there are many that are dedicating very serious resources to hacking and surveillance because we know that there's real political and socio-economic value to do so. They might be monitoring political opposition, influencing elections, stealing secrets. Just to give you a sense of how big these threats are, I wanted to plot here the operating expenses of the seven biggest tech companies in the US. So operating expenses will include everything from R&D to rent to hiring their sales and marketing team. And you might internally ask yourself the question, well, how many cents on the dollar out of this operating expense budget goes towards security? Generously, maybe 1 out of 10. This is the annual budget of the US National Intelligence Program. Now, the size and the scale of intelligence operations in each country is unknown. We know, though, that if you're worried about nation states attacking you, these threats operate on a different scale than the companies that we rely on to protect us. And in fact, we know that we cannot protect ourselves just by outspending nation state actors. We need to fundamentally change the way that we think about how we approach security. I also want to give a sense of breadth here because we're not just talking about the US and their intelligence programs. We know that all around the world, there are countries that are dedicating resources to this, and it has real implications on civil society. The Freedom House does an assessment of online freedom every year where they score things like internet censorship, free speech, free press, and surveillance. And while we've been frightened about the levels of national surveillance in our own country, in the US, over the past couple of years, it's important to remember that we still live in this green bubble and that things can be quite different depending on where you are in the world. And I believe it's important that we provide ways for people to communicate anonymously online because we know that today people are being attacked, arrested, and killed for expressing certain opinions online. So I believe, as computer scientists and engineers, we have a moral responsibility to build technologies that protect basic human rights and freedoms of everyday citizens, regardless of where they live and what governments they have in place. So technically speaking, let's ask the question of how do these threats attack user privacy in the first place? Well, here's a high-level diagram of nearly every modern application. We have clients on the bottom. They'll connect through the internet or some network to the cloud where they'll access their application and their data. And I'll represent the cloud as this treasure chest because the bottom line here is that for the first time in human history, everything that can be known about a person, that's everything from their personal communications to their location to increasingly now a live video feed into their home, all of that can be found in a single location. So on the network, there are real commodity boxes that are being sold today that allow anybody to be able to do deep packet inspection and traffic classification at line rate. And that can be used to filter, surveil, misdirect, or fail connections in real time. And anybody can buy a box and do this today. Secondly, no individual or company, regardless of size, is immune to the threat of malicious hackers. And it boils down to the fact that if you believe that there's no such thing as perfect code, then with enough time and enough resources, someone will be able to find a flaw and be able to break in, leading to a wide range of impact from service disruption, covert surveillance, website defacement, and the one we're probably all too familiar with, massive data breaches. And due to the fact that hacking now does have a black market, it is increasingly becoming commoditized and easily done uh, with a certain number of resources. Lastly, it's important to remember that the cloud is not some abstract thing somewhere. It's a physical thing that lives in a real data center, and that real data center lives in a real country governed by real laws. So, depending on where the data center is, a cloud could be subject to mandatory surveillance partnerships. They could be compelled to give information about individuals, or they could be compelled to censor content directly at the source. So here we see a threat that spans all sides of the system, and we need to ask now, what security model can possibly protect users from these types of powerful threats? Well, there are a lot of current efforts today that predominantly focus on expanding the use of encryption. And in fact, we increasingly do use encryption to, for example, use TLS to connect to a web service, the connection to the web service. And if we're lucky, the cloud service might encrypt the data before it's stored to the database. And while encryption is important, I think it's clear that encryption on its own is not enough, because it doesn't necessarily protect the users from hacking and censorship programs and surveillance programs. So you can look at this diagram and think of it as a framework for both the work that I've done and the work that I plan to do. In the rest of this talk, I'm going to briefly first describe uproxy and radiatus, uproxy being a censorship circumvention tool to get around internet censorship, and radiatus is a web framework for hardening web applications from external intrusion. But I will spend the majority of my time talking about TALC and my vision for oblivious cloud services, which I believe to be potentially a way to address all of these threats at once. What's cool about this work is that we've built real systems and working code in each one of these spaces, and we've shown that these systems can work in practice. In fact, uproxy has been deployed to tens of thousands of users around the world, and while it's important to remember in all of this that there's still a substantial amount of work to be done in each one of these spaces. I'll briefly want to acknowledge my collaborators. I couldn't have done this without the great help and advice and mentorship from a wide range of very talented people across various institutions, and I thank them for their help. So first, let's talk about uproxy. It's clear that internet censorship is a pervasive problem. There are numerous organizations that measure this, and the high-level fact is that over 2/3 of all internet users live in countries where censorship exists. So even if you use HTTPS to connect to your web service, it's trivially easy to block all traffic to particular destinations. So in this case, the threat model is you have some network censor that controls the network in your country, but it's limited to a single country, and for the most part, it's generally open, but the censor maintains some form of blacklist of sites to block. Now, a common way to get around this is the notion of a centralized proxy or a VPN server. So if you can find a proxy that's outside of your country, ideally in a country where the website is not blocked, then if you can create an encrypted connection to the proxy, you can use that as a relay to forward your traffic to the site that you actually want to go to. Now, there are two high-level problems with centralized proxies. The first of which is trust. The user needs to be able to trust the proxy. In fact, we've seen instances where governments will hand out free proxies, and they'll use that as a mechanism to keep track of people and attack their connections, steal passwords, and come election time, they might use that position as a proxy to be able to block and manipulate pages. Secondly, the proxy also needs to be able to trust the users. They need to be able to trust the users not to be doing illegal activities off of their proxy. I think the more fundamental problem here is a problem with scale, and the fact that these proxy services are just as blockable as the sites they're trying to help gain access to in the first place. So if they get big and become noticeable, well then it's just as easy to block these types of VPN services or proxies. It turns into a giant game of whack-a-mole. From the censor's perspective, they'd like to be able to see a small number of proxies and have a big hammer to be able to block all the types of ways around their censorship. And that's the world we live in today. I think from the user's perspective, though, it'd be nice to have a lot more proxies. In fact, make it cheaper and easier for users to make their own proxies, such that it can become hard to whack them all. And that's how we started the uproxy project back in 2012. And the intuition comes from this observation that there were a set of students at universities that would set their own uproxy servers. So they would find some technically savvy friend, ask them to set up a proxy server for them, and then they would share that password around. Now, the problem with this is that it's limited to friends with people that have friends that are tech savvy. Uproxy tries to encode this pattern into a piece of software. So uproxy is a software bundle that packages both a proxy server and a proxy client that is trivially easy to configure, even for non-technical users. And then we make it easy for users to connect to each other and find each other through social networks to be able to handle the access control. So uproxy is a system for do-it-yourself censorship circumvention, and we address the trust and scale problem in a rather unique way. First of all, with respect to trust, trust is explicit. You're connecting to friends through a social network, so there's no confusing access control configuration policies. You're just explicitly granting consent through a social network, and by doing so, you know exactly who you're dealing with on both sides. From the scale perspective, we make it trivially easy to install and operate a proxy server, even for non-technical users. And from that perspective, it becomes hard for a censor to find all the proxies on the network. The goal here for uproxy is to build a tool for self-empowerment. We're not trying to build a service, but rather build a tool for users to be able to help themselves. So what we ended up building was a product for Chrome, Firefox, and Android. In fact, we wanted to make it useful to a large range of users, and we wanted to port it to a number of different platforms to make it easy to connect to friends. In doing so, we had to tackle a number of networking systems challenges. In fact, we built a complicated, sophisticated networking stack in JavaScript that used some modern networking protocols like WebRTC, and in fact, we even built a JavaScript based network level obfuscation system to be able to manipulate packets before they're sent out on the wire. Furthermore, there's some interesting HCI challenges here because for non-technical users, it's quite hard to make networking intuitive. So we spent a lot of time designing good design and linear flows for users to be able to easily connect to their friends and set up networking routes. So what you see here is some screenshots of our software. In the second screen, users can connect to social networks and find their friends. And in the third screen, we show that we also provide the ability to be able to create an account on a cloud service like DigitalOcean and push to deploy your own personal VPN service out that you can share with your friends as well. So we built this system. It's software you can download and use today. In fact, I have it installed on my cell phone and laptop. Go to this website if you'd like to check it out. You probably know a friend or two who live in censored countries with censored internet, and I encourage you to give it a try. With generous support from Google, we currently have a full-time team that continues to work on it and related offshoot projects. But there are a lot of interesting research problems to continue to pursue here. In fact, we want to make it more valuable to more people, so we want to take a look at other ways of making it harder to block, such as network obfuscation. All right, now we're going to switch gears a little bit and take a look at Radiatus. So uproxy was a system to address how to maintain connectivity to the cloud in general in the face of a network censor. Now we're going to move on to another challenging problem, which is that of addressing remote hackers. So if you're a famous person today, you're going to be the target of an attack. Even if you have a large IT department on your side, there's a bunch of interesting challenges here. So we're talking about, for example, emails and photos that you might have stored in the cloud. In this case, you might trust the cloud provider, but if the attacker can break in, well then perhaps they can get access to everything that they want. So the threat model here is predominantly focused on external attacks, such as code injection, SQL injection, buffer overflows. Here are attackers living somewhere on the internet that can submit arbitrary network requests to your service. Now, to get a high-level understanding of why web applications are so vulnerable to hacking today, here's an architecture diagram of nearly every web service that exists out there. And I believe this to be a fundamental problem of how we design web apps today. So on the bottom here, we have a set of clients highlighted in orange, and they can be living anywhere on the internet. Now, they're going to be submitting requests, generally HTTP requests. And in blue here, I show everything that lives on the server. So there'll be some load balancer that spreads the requests across some set of web servers. These web servers are all running identical logic, and this logic is a global application logic that will interpret the HTTP request, log the user in, potentially fetch content from a set of databases, assemble a page, and return that back to the user. Now, I highlight in blue because it's also the case that everything that's on the server is part of the trusted computing base. So from the developer's perspective, they are responsible for properly handling requests, administering access control, preventing information leakage. Any vulnerability in the server-side logic might lead to access to global data. And for these reasons, remote code execution is actually particularly bad. One vulnerability could give you root access to nearly everything in the web service and give the attacker the ability to run code as a developer. Now you might ask the question, why are web apps built this way? Well, it's important to remember that web apps are built and evolved from this long history of HTTP parsing libraries. And from the developer's perspective, this is nice because it leads to cheaper and faster and rapid development cycles. But what we'd like to be able to build is a system that is much more robust to attacks without compromising too much on programmability. So the Radiatus work, we wanted to ask the question, suppose we assign a sandbox process on the server for every user, and we call this the user container. And now we'll design an architecture around this. We call this shared nothing, because in contrast to the way that web apps are currently built, where application logic has global access to the database, in shared nothing architectures, the sandbox only has access to the code and the data for the user that's currently logged in. Now, this has the potential for potentially limiting the impact of vulnerabilities, even 0 days that we're not aware of. Because even if an attacker is able to exploit a vulnerability, well, they'd be limited to that sandbox for which they have credentials in the first place. So what does this look like architecturally? Well, as I mentioned, every user is going to be assigned an isolated sandbox in the cloud, which we represent in these white boxes on the server. So the user now, instead of being sent to a load balancer, they'll first authenticate against what we call a user router and be assigned a session token. Now with that session token, we're going to enforce at the network layer that any network request that comes in from a particular user will be strictly routed to the sandbox for which they were assigned. In addition to that, within the sandbox now, they'll have access to a set of APIs to be able to store data to a database, and we'll furthermore build this thing which we call a storage guard, which we place in front of the database, which exposes virtual isolated partitions to each one of the users. Now we want to be able to use existing databases because there's a long history of scalable, consistent, fault-tolerant databases that we want to leverage. But we want to be able to protect that with this access control mechanism which we have in the storage guard. Now notice here we've minimized the trusted computing base to the user router, the runtime environment, and this storage guard in the database. And all of this will be shared across all Radiatus applications. But any code the developer will write will run inside these sandboxes. So now, if an attacker comes in, well, they'll authenticate against the user router, and due to the way that the network routing works, any compromise in application logic will only be limited to the sandboxes for which the attacker has credentials. As a consequence of this architecture decision, we need to solve a set of other problems to make it work. Suppose we had a service like GitHub or Dropbox where there's a lot of data shared between users. There's high-level questions like, how do we restructure an application to support sharing and storing of data? How do we reduce the cost of redundancy on the server? And how can we do this in a way that's compatible with scale? These are challenges not solved by existing solutions based on service isolation. So in the paper, we describe a cheap message passing mechanism based on distributed capabilities, and I'll refer you to the paper for the technical details. But at a high level, we showed that for the most part, the probe framework scales linearly. In fact, we can horizontally scale web servers and linearly increase our throughput. And it shows that we were able to prevent most of the severe web-related vulnerabilities in the National Vulnerability Database when we translated it to our framework. Now, there is a cost and a trade-off. The main cost, as you can expect, is memory. But we calculated that to be on the order of a few pennies per user per year. There's also an explicit programming cost. Think about explicit data sharing between users instead of a global database. Now, there's this additional programmability challenge of explicitly passing messages between users, which comes at a little bit of a programmability cost. But there's a research implementation that exists. You can download and use it. But what I would suggest is that if you're going to build a website today, I would consider alternative architectures for higher security. So Radiatus shows us how to build secure web services from external intrusion, assuming that we trust the cloud. And for the foreseeable future, this will be important. But for now, I'm going to go in depth on a certain class of applications where we can design cloud services that function even if we don't trust the cloud. So far, we've been talking about applications where the majority of the application logic lives in the cloud, as well as storage, and the client basically just renders a view and gathers user input. And from the cloud provider's perspective, perhaps safeguarding security is all you really care about. But what if you didn't want to trust the cloud? Perhaps you are afraid that hackers might gain access, or you might be afraid of the government spying on you. Well, in that case, it would be necessary to make it possible to build applications without explicit trust in the cloud. And in doing so, we want to make clouds opaque to the data at all. Now, there are some set of applications where we can move out of the cloud entirely. So for games and mobile-first social networks, assuming that you trust the user device, we can try to split the application logic and storage and push it down into the client device. And in fact, increasingly we're starting to see intelligent mobile apps do more and more of the application logic in the device. But there are a set of things that we still need the cloud to do. For example, mobile clients may not be online all the time, so we still use the cloud to synchronize state between devices. And for that purpose, the cloud needs to store data at least temporarily. Secondly, the client device might be lost, so we typically use the cloud to back up the data to be able to restore devices when we lose our mobile phone. And lastly, analytics across all users and all devices is still important from a developer's perspective. So that leads me to the vision and picture of oblivious cloud services. What I'd like to be able to build is a set of cloud functions to do the things that we need the cloud to do today, such as store data, send data, search, collaborative filtering, machine learning, serving applications, ads, etc. But I'd like to be able to design these cloud services and co-design it with a client-side library that's linked to existing applications. So this library should expose a set of interfaces to the application that the application already uses today. If you've ever used something like AWS SDK or Azure SDK, there's a set of cloud functions that we expect the cloud to do that applications already use these interfaces to integrate with the cloud. Now, this library will send useful requests, response, and do useful work with the cloud service. But ideally, from the service's perspective, all it sees is random noise, such that now the consequence of this is even if you were to instrument all of common infrastructure from the internet to the cloud, well, if all the adversary sees is noise, well then provably we can show that it yields no information. There's nothing to be learned by instrumenting the cloud. So by treating the cloud as entrusted, we want to build cloud services that are secure by design. And in doing so, remove this giant attack surface that we've generated that's the cloud and the internet today. So the first step towards that vision is a system called Talic, which is a private publish-subscribe system. We use publish-subscribe today every day, whether you know it or not. And it basically describes a general communications pattern. So for example, Alice and Bob might be communicating through the cloud, and Alice might be publishing messages into a chat thread which Bob will subscribe to. Alice might be publishing images and tweets into a newsfeed, or a set of calendar operations into a shared calendar, or a set of moves into a game, or a set of configurations into a set of IoT devices. At a high level, a lot of what we use the cloud for today is just shuffling around data, and we can model that as logs in the cloud for read-write workloads. Now, something that we already try to pursue today is end-to-end encryption. We can encrypt the messages between Alice and Bob to protect the contents of the messages. So if you've ever used an application like Signal, we can hide the and we can hide the contents of the information in the message to achieve confidentiality. Now, a curious cloud, though, can still log all network accesses, and that exposes a lot of information. For example, if Alice and Bob are encrypting their messages, but they're depositing those messages in the same chat thread, well, then we know that Alice and Bob are communicating. And in fact, communications patterns can yield very rich information. It can reveal which users are sharing data with each other, when traffic is sent, where traffic is sent to, how much is transferred, and if you listen long enough, potentially the adversary can infer the contents of the communication. Now, for some people, like journalists, activists, dissidents, and protesters, protecting this is critical to their safety and livelihood. So let's talk about this in the context of an explicit example. Let's say, for example, Alice is a source who wants to share some data with Bob, the journalist. Now, as I mentioned earlier, if they both deposit messages into a cloud in country X, well, that reveals common contact. And if you just shuffle around where the data storage is, well, it yields the same problem. A common thing that we do today is to use this notion of a relay. So if I were to find a relay in a separate country, and I were to encrypt the message to the relay, which then encrypts the message to be stored into the database, well, maybe I can obscure where this message is coming from. And you can think of Tor as a more generalized version of this. Instead of using a single relay, we might use 3 to 5 or any number of relays in any number of countries before we end up depositing the message in our database. Now, journalists do this today, but there is a fundamental problem with this, which is that of traffic analysis. So if I can watch on the network when Alice is using the system, and I can see the database on the other end and see which messages are being modified, then over long periods of time, in what's called an intersection attack, the adversary can develop a statistical model of who's likely to be communicating, because every time you send a message, that leaks just a little bit of information. And over long periods of time, you can still develop with high probability some model of who's communicating with each other in the system. Now, it's unclear whether or not the powerful threats I described has this capability today, but we'd like to be able to build something stronger with provable guarantees. So Talic is a private publish-subscribe system for sharing data through untrusted clouds. We want to hide both the data contents of the messages, but as well as the communications patterns. And we make this practical using two techniques, which I'll soon describe, called oblivious logging and private notifications. Now, we've built a system, and we've shown that we can achieve 3 to 4 orders of magnitude better performance than the closest related work. So from a security perspective, we want to have a very strong security goal based on indistinguishability. Now, informally, what that means is that 2 access sequences from a client looks indistinguishable to the adversary. So if I were to be sending messages to a specific person, or if I were completely idle and not doing anything, or if I was sending completely random traffic out on the network, all 3 of these instances or scenarios should look indistinguishable from the perspective of the adversary. So to get an intuition of what this will look like, well, if every single client on our system is periodically just sending random noise, and if you can embed real requests in the schedule, which still looks like randomness from the perspective of the server, then regardless of how many of these requests are legitimate versus just dummy requests, well, we achieve our security goal. Now, in addition to a strong security goal, we'd still like to have a set of systems goals to make this practical. So from the perspective of the system, we'd like to make it mobile friendly. We want to make it very little computation and network costs in order to send a single request and receive a response. So every real request and response should require only one message. We want to make the system relatively efficient to be able to support thousands or tens of thousands of online users sending a message every 5 seconds from the perspective of a single machine implementation. And ideally, we'd like to be able to design it in a way that is scalable. We'd like to make it general purpose to support the application workloads I described earlier, and I'd like to make it relatively low latency, on the order of seconds, to be able to support messaging workloads. It's important to remember that no system today does all these things at once. Now, the system isn't perfect, and there are a set of limitations that I won't describe in this talk. So for example, In the protocol I'm about to describe, even if a single cloud becomes inaccessible to the user will not be able to access the global system. And now there are ways to mitigate this, which we'll discuss in future work, such as hosting it in highly available cloud services or using fault tolerance mechanisms to be able to survive any loss. But I won't describe these mechanisms in this talk. Now, our threat model has one big assumption, which is what we call the antitrust threat model. Suppose we had access to a multitude of different cloud providers, each run by different organizations, each living in a different country. So this application might be configured with somewhere around, say, 2 to 4 independent clouds, and we can assume each one of these clouds is logging everything about user requests, like the source, the type, the parameters, the timing, the size, everything. And they're all trying to build statistical models of who's communicating in the system. Now, the antitrust threat model says, let's assume that not all of the clouds are controlled by the same adversary, but we don't know which one. So for example, W, X, and Y might be all colluding to try to share information to determine who's communicating with who, and de-anonymize users. But as long as there exists some country Z that's not colluding, well, we can leverage this assumption to achieve practical performance. And I think there's reason to believe that this is a reasonable threat model today with current international law enforcement agreements. To flesh out our threat model a little bit more, we're assuming that there are small groups who trust each other and want to share data together, but they don't trust the cloud. And in addition to that, there are malicious clients who are attacking both the honest users and attacking the service. So to start, I'm first going to begin by describing private information retrieval. Now, I didn't come up with this. This was designed in the 90s under the same threat model I described earlier, and it provides a mechanism to retrieve data without revealing which piece of data you're interested in. So let's first assume that all servers have an identical copy of the database. So in this example I'm about to describe, let's say there are 5 buckets of data of equal size, and there's a client on the network that wants bucket 2. And that's the secret. We don't want the servers to know that the client cares about bucket 2. So we encode that in a secret request vector Q prime, which is a set of zeros except for a 1 in the position for the bucket that we want. So the way that the protocol works is, in the first step, we'll send completely random bit strings to the first n-1 servers. For the last server, though, we'll take a linear combination of the noise we just generated and the secret request vector. So we'll combine them using exclusive OR. And you'll notice that because we're padding the secret with completely random noise, this should not reveal any information to the last server. Now, from the server's perspective, each one of them will, in parallel, scan the request vector and scan the entire database. And for every position where there's a 1, it'll return that bucket and combine that into the response. So for example, the first server will return back buckets 0, 1, 2, and 4. The second server will turn 0 and 2. And the third server will turn 1, 2, and 4. Now what you'll notice is that when the client combines all these responses, well, what it wants just naturally falls out of the system. And this has some really nice properties. From the perspective of the client, I only need to send one request vector to each server, and I only need to retrieve one response, which is approximately the size of a bucket. From the perspective of the server, as long as they're not all colluding, the requests and responses all look random. But there are some limitations which we need to overcome. The first of which is that it's clear that reads are expensive because every single read request will require a full scan of the entire database. So as the database grows, the cost of a single read will also grow. It also requires equal-sized buckets and consistent snapshots across all servers, and clearly it's only a read-only protocol. But it does give us some intuition for how we will achieve client indistinguishability. So for example, if every client always does a PIR request regularly, and these PIR requests look random from the perspective of the server, well, in that case, it really doesn't matter how many of these PIR requests are for things that you actually care about, or for completely random buckets. Well, it achieves our security goal because from the perspective of the server, all of it looks identical. So this is the prior work. And now I'm going to describe the contributions of Talek. How do we design a pub subsystem around this primitive? So at a high level, this is what our system looks like. We first, as I described earlier, expose a client-side library, which we call libtalek, and that's linked against the application and exposes a publish-subscribe interface. Now, the client or the application can call publish and subscribe, but critically, each one of those calls should never actually directly trigger a network request. Instead, we queue those into read and write queues respectively. Now there's a periodic process which will look in each one of these queues, and if there is a request, dequeue it and generate a privacy-preserving network request. And if it's empty, it should generate a dummy request that looks indistinguishable from all the legitimate requests and vice versa. So every client here needs to act identically from the perspective of the servers. And furthermore, these writes need to look random. So every parameter in the request must also be random and equal sized. So now I'm going to describe oblivious logging, which is a protocol in Talek that enables the servers to operate on what looks like random noise while delivering pub sub functionality. So the high-level questions we need to answer with oblivious logging are these 5. The first of which is, how do we bound the cost of a PIR operation? It's clear already that PIR is going to be the bottleneck in our system. How do publishers write in a way that looks random? And furthermore, how do the subscribers find these messages on the server without coordination? How do we deal with write conflicts on the server? And how do we keep all the servers consistent? So the first thing that we're going to do is we're going to fix the size of the server-side state. So the problem here is if we continue writing and writing and writing, well then the server will store an infinitely growing set of data, and as such, the cost of a single PIR operation will also scale linearly with the size of the database. So what we'll first do is we'll just say, let's only store the n most recent messages on the server globally. What we're going to do is we're going to bound the cost of a PIR operation by configuring the size of the database. And that value for n now needs to be big enough so that clients can retrieve messages before they're garbage collected. So more explicitly, what this looks like is the table on the server side is going to be arranged in a linear table of size n. And when a write comes in, the write will specify the bucket to place the message in and an encrypted message. In order to satisfy our constraint to only have n messages, we're first going to remove the oldest message before we insert messages at the specified bucket. And we'll have clients insert messages at random buckets. So the way that we're going to make writes look random is we're going to first encrypt the messages with randomness using a CCA secure encryption algorithm. And we'll have the client specify a random bucket to put the message in. Now, in order for publishers and subscribers to agree on where to look, we're going to borrow an old idea from military radios called frequency hopping. So for every single topic or log, we'll have something called a secret topic handle. And that secret topic handle is a pre-shared secret across all the publishers and subscribers in a single group. Now that topic handle will have both the topic ID, an encryption key to encrypt our messages with randomness, and something called a seed. Now that seed, when fed into a pseudo-random function family, for a particular sequence number, it'll generate this deterministic sequence of buckets, which we call the log trail. Now, with this topic handle, a publisher can, for each message, a sequential message in the log, it'll deposit these messages in this deterministic sequence in a way that looks random to the server. So without the topic handle, to the server, these writes look like they're going to completely random buckets. But the clients, because the subscribers also have a copy of this topic handle, they know where to look. And they can use PIR to pull and read this table to privately fetch the messages that they care about. So this is how we achieve zero coordination. As long as you have this secret topic handle, publishers and subscribers don't need to coordinate to know where to place messages and where to look. But this must be kept secret from the adversary. Now, on the network, we start to see how these rights start to look indistinguishable. When there are no rights, we'll generate these dummy requests, and we have this notion of an idle seed and an idle key to generate a random bucket and a random payload. Now, when there's a real right, we'll use the topic's seed and handle to be able to generate the next bucket and to encrypt the message with randomness. And due to the cryptographic properties of pseudorandom function families and CCA secure encryption, both dummy and legitimate requests look indistinguishable from the perspective of the adversary. Now, how do we handle conflicts? What you'll notice now is that this server-side state starts to look a little bit like a hash table. And traditionally in a hash table, you might use the linked list at every single bucket. So if there's a conclusion, we'll just append that message to the linked list. But this won't work for PIR because PIR comes with a constraint that every bucket needs to be of equal size. So we'll borrow an idea from cuckoo hashing. Now, instead of specifying just a single bucket to put a message in, let's say we can specify 2 buckets. And the client will say, well, the server can choose which of these 2 buckets to put the message in. And subscribers, on the other hand, will need to poll both buckets in order to find the message. So the way that cuckoo hashing works is if one of these buckets is empty, we'll just place it in that bucket. But if both buckets are full, then we'll randomly choose one of the buckets to put it in. And the message that was originally in that bucket, well, we'll evict it into its alternate location because every single message is associated with 2 locations. Now, the rights are guaranteed to be in one of 2 spots. It's just that the server chooses which. So the client now, when they're doing PIR probes, might need to probe both locations to get the message. So we'll augment our oblivious logging technique now with 2 seeds in the topic handle, each of which generating 2 unique but deterministic pseudorandom sequences of numbers and buckets locations. So now, for the first message in our log, it might be here or here. For the second, there'll be also 2 locations. For the third message, there'll also be 2 locations, and so on and so forth. Now, there's a theoretical limitation to cuckoo tables, which is that traditional cuckoo tables like this have a maximum load factor of 50%. What that means is that we have to allocate a table that's twice as big as the number of messages that you want to put in there. Now, this is not optimal for PIR because PIR reads require a scan of the whole table. So now this makes it more expensive than it needs to be. What we would like is a table that's much more dense. So we'll introduce a variant of cuckoo tables called blocked cuckoo tables. And instead of having just a linear array, we'll now have a table or matrix of B buckets, each of length D. So for each bucket, we have a FIFO queue of D entries. Now we have the same greedy algorithm for balancing conflicts. So if any one of those 2 buckets in our right has empty capacity, we'll just put it in there. And only when a bucket becomes filled up will we evict a message into its alternative bucket location. What's nice about blocked cuckoo tables is that it has a much higher load factor, which means that the table can be much more dense. So for higher values of D, for example, in our implementation, we configured it to be around values of around 4, it can achieve densities of over 95%. So this reduces the cost of a PIR operation almost by a factor of 2. We can have a much more dense table, still handling write conflicts, but the table, because it's smaller now, every single PIR operation is much cheaper. Now, this does come with a trade-off that a PIR operation, when reading a bucket, now needs to retrieve a little bit extra more data than it needs to be. But it does come with the benefit that we can have much higher read performance. So the way that we achieve dense data structures is that blocked cuckoo hashing handles these write conflicts with much higher density. Now there's one final problem in terms of correctness, which is consistency. As I mentioned earlier, each one of these clouds needs to have a consistent snapshot of the database. And that's even more important in the case of cuckoo tables because we need to make sure that messages are inserted in the same order, such that evictions happen in the same order, such that all the cuckoo hash tables look the same from the perspective of all the servers. So what we'll do now is we'll arbitrarily choose one of the clouds as a leader, and the rest of the clouds as followers. So when we do a write, we'll send that write to the leader. That leader can specify a global sequence number and forward it to our followers. And by doing so, with a global sequence number now, everybody knows which order to put the messages in, so we can achieve consistent state across each one of the clouds. Now, to preserve the correctness of PIR, we need to encrypt each read to each one of the servers before we send it to the leader. Now, this also reduces client bandwidth because we only have to send one request to and one response back from the leader. So these leaders now are enforcing consistency by using timestamp ordering to achieve sequential consistency. To sum up, in terms of indistinguishable writes, we now have two buckets and a payload, and because we're specifying the bucket number from the result of a pseudorandom function family, and we're encrypting the payloads with CCA secure encryption algorithms, due to these cryptographic primitives, all dummy and legitimate requests look indistinguishable. From the perspective of reads, well, now when we send a read request, we'll encrypt these PIR request vectors with the public key of the respective server, and by doing so, we can also make these dummy and legitimate requests indistinguishable. Now, in terms of correctness and the security goals of our system, we have created a functioning publish-subscribe system. But there is one last performance characteristic that we want to be addressing, and that's of scheduling. When it comes to scheduling writes, it's clear. If there are messages to be written in a write queue, we'll write it, and if there's nothing in the write queue, well then we'll just write something random. But from the reads perspective, it's much harder. So if I'm subscribed to a number of topics, and let's say, for example, I might have a lot of people that I'm following on a particular application. Well, those are all separate topics that I need to check, and I don't know when a new message exists on that topic. So in that case, in the naive way, I might have to do round-robin polling for each topic. What I would like is a digest that combines something from the servers that will tell me which messages exist on each one of the servers so that I know which topic to be polling. So in private notifications, each one of the servers can send back what's called a global interest vector. And these global interest vector will privately encode which messages are currently readable on the server. Now, crucially, this has to function in a way such that the servers, again, don't know anything about the messages that actually exist on the server. But this global interest vector can internally be used by a client alongside the topic handle to be able to enumerate all the topics that have changed and use that to prioritize reads on the read queue. Now, I'll skip the details of this in the interest of time, but Talik looks like this from a high-level overview, which is that we're periodically getting updates to get this global interest vector that'll help us prioritize reads, and we're also doing writes periodically. Now, for our experiments, we actually run each one of the servers in an AWS EC2 cluster. Of course, in a real deployment, we would want each one of these servers to be existing in a separate cloud in a separate country. But as I mentioned earlier, it turns out that PIR turns out to be the bottleneck, so this is much easier for us to debug and gives us a reasonable notion of the performance because the latency turns out to be not a crucial factor in the performance. So we have 3 servers on AWS EC2, each with K80 NVIDIA GPUs. We're simulating tens of thousands of real clients, and these clients are each sending and receiving messages every 5 seconds. The first thing that we did is we highlighted the performance differences between our system, in terms of our read and write performance, to 2 of the state-of-the-art private messaging systems, and we plot that on a log scale. And the first thing to quickly note is that we achieve 3 to 4 orders of magnitude better performance than the state-of-the-art related work that's out there. For Pung has a much stronger threat model. So in this case, they don't have the antitrust assumption. In their threat model, they don't trust anything outside of the client device, but that leads them to a set of design decisions, such as using computational PIR as well as some different data structures that leads to much slower read performance. Riposte is some of the state-of-the-art work in practical anonymous message broadcast. They have the same threat model that we have with respect to antitrust, and they come up with this interesting mechanism for PIR, which they call PIR in reverse, for doing writes that look anonymous. Now, we show that oblivious logging is much faster, leveraging trust between the publisher and subscriber. We also wanted to measure the performance of a single machine implementation. So this is a single server in each one of the independent clouds, and we scale up the number of real clients, each sending messages. And we show that there's about linear growth in performance until we become bottlenecked by the PIR process. So what you'll see here is that we're achieving on the order of hundreds of thousands of messages per minute with tens of thousands of clients. And for each one of these lines represents a different size of the database, a different value of n. And so as the database is bigger, that leads each PIR operation to be more expensive, which leads to lower throughput. But we're still talking about on the order of hundreds of thousands of messages per minute. So it's written in Golang. It's about 3,000 lines and growing. We have a CPU version and a version with GPU acceleration. It's currently a single machine implementation, but a distributed version and a scalable version is on the way. So this leads us to the future work. So there's a lot of work in terms of how do we make this better, and there's some interesting challenges from a research perspective on how do we do that. The first thing to think about is how do we address scaling with privacy-preserving systems. We can't just traditionally partition the database like we would a traditional database. In fact, just sharding naively might actually leak which group of messages you care about. So it's interesting to analyze the future work in the space of co-designing the security protocol with distributed, horizontally scalable architectures in a way that's fault-tolerant. So there's some interesting work in how do we build scale-out architectures for these privacy services. I also mentioned earlier that PubSub is just one of the things that we rely on the cloud for. We also need storage, machine learning, analytics, and search, and there's some interesting work in building practical systems to serve realistic workloads with good performance in a way that we can support each one of these functions that we need the cloud for today. And lastly, these cloud services are only as important as our ability to incorporate it into the applications that need it. So, for example, in Talik, we made some assumptions like fixed message length or fixed rate of messages, and in reality, this might impose some usability cost on the user. So there's some interesting work in studying real application workloads to reduce the usability costs of integrating these types of privacy-preserving services into the applications. And there might be some programming languages techniques to help us reason about the privacy leakage in an application. All these are towards the final goal of building practical cloud services that protect user privacy from powerful threats. My hope is that in the future, we'll treat stronger notions of user privacy the same way that we think about encryption, just a necessary element of a well-designed system.